So let me record the screen. Now we're ready. So the first thing that I want to mention is that hopefully you have R and RStudio. So they are different. They are basically the same. So they work with R language, but RStudio it's more friendly to work with. I think that is like a nicer graphic interface. And let me check.
Uganda. Hey, up and down. That's the boy kind Mareta.
Okay. Yeah, please mute yourself because you know I have to look for which microphone is open to mute that microphone, and that is going to take time. So yeah, as a again, RStudio is just nicer to work with, and hopefully you have a RStudio now in your computer, and we are going to use an R Markdown. So this script it's in the website, and you can follow that script. I changed some things tonight, the last night. So I'm gonna update the script after this session. It's pretty similar. I just put some comments and edit some yeah, I did some edits, and hopefully now it's just easier to read the script. And we're gonna work in R Markdown. R Markdown is great to do reports and to export the R code and the graphics in a format that it's easier to share with more people. And yeah, so the first thing that I want to show you, hopefully you saw, so this is not an R tutorial. Hopefully you watch the tutorial that I put in the website. There are dozens of tutorials in R. So I just gonna go into the code to simulate some data. So the good thing is that we don't have to load any data into the code. We're just gonna simulate everything. So the first thing, and I try to put the comments into the command lines that I thought that were relevant. So the first thing that we are gonna do here, for example, is remove everything from the environment, the global environment. So R has a global environment where we are gonna store all the information that we are gonna produce in our code. And for example, here I'm gonna produce the allele frequencies of P, and you can see here that now we're gonna have JAT in the allele frequency. So I just mentioned that because I'm not sure about if you are familiar with R or if you are new in R. So as you can see, each time that I store a object in R, that is going to be in the global environment. So with the remove command, basically I'm just going to remove everything, and that is good if you want to start with a new analysis, just because if you have object from another R project that maybe can make a mess with your data. So now, as I told you, I'm gonna use this script to show you some concepts that we discuss in the videos. And so the first thing is the allele frequency. So we're gonna work with the allele frequency in this example, 0.5. Then also in the videos, we mentioned that the population size is really important. So here we have a population size of 10,000 individuals. And another thing that we mentioned in the videos is that we're gonna have a additive, we can have additive or dominant effects in the alleles. So what we're gonna do here is that we're gonna simulate 3 alleles. The first 3 locus, sorry. So the first locus is gonna have an additive effect in the phenotype of a 1000. Let me. Okay. An additive effect of 1000 and a dominant deviation of 0. So remember that with the models, we try to capture the additive effect, that is how the one allele, the dominant allele, is going to increase the phenotype in the population. So with a linear regression, we can estimate that. And the deviation of that additive effect is because dominant. So here we're going to have one locus that have an additive effect with a 0 deviation of dominance. So this allele have a complete additive effect. Then the second locus that we're going to simulate have has a dominance effect, a complete dominance effect. And remember that when the dominance is complete, the heterozygous lines have the same phenotype that the homozygous lines for the dominant allele. So here, as you can see here, the additive effect in the locus A, it's 800, and the dominant, it's the same, that is 800. So here we just have the dominant and the additive effect for locus 1 and locus 2. If you have questions, please let me know. And then to simulate the phenotype, we need the mean of the population. So what is going to be the mean of the population? I just use a 5000. Any of these data have like it's simulation, so that I just put some numbers there to show you the concept. So that doesn't have any relationship with the real world. So I put just 5000 markers. So we're going to simulate 5000 mean, a mean of 5000. So we're just going to simulate one phenotype with a mean of 5000. And another concept that we discussed in the videos was the heritability. Remember that the heritability is the variation in the phenotype that it's explained because genetics. So the variance of this phenotype, the genetic variance, the variance of this phenotype that is going to be explained because genetics is going to be 50%. And here, this part is start a little, yeah, Anthony, do you have a question?
Yes, please.
Yep. Go ahead.
Thank you. Which heritability are we dealing with at this level? Is it broad heritability or?
In this case, it's broad because I'm gonna use this heritability to predict the phenotype. So the heritability that I just said here is gonna control all the genetic components in the phenotype. So it's a broad. Okay, that is a good question because when we're gonna do the simulations, we are gonna check that heritability to produce the environmental error. So everything that is not gonna be genetics. Okay, so now we have we have the additive effect, dominant effects, we have the mean of the population, and we have the heritability of this trait. And now we have to produce the sampling genotypes under, actually, I don't know, I am not running this thing. So to run that, we just have to step in every single line and enter. So now we have to produce the genotype for the 3 alleles. So remember that we are going to simulate 2 alleles, one with additive effect, another one with a dominant effect, and another one that doesn't have any effect in the phenotype. So that is why I didn't specify a additive or dominance for the last allele, the last locus. And then we have to simulate that genotype. So in the genotype, we are going to use this function in R. So that is an R-based function to produce the number of lines that we are the population size, the number of data that we have in the population size, and with the probability of P that is the allele frequency. And if you run that, you are going to have the genotypes in your population. So Antoine, if you have more questions that you have you raise your hand, or that is for the same question that you just did?
Oh, sorry. I thought. Okay. I'm fine.
Okay, yeah.
Thank you.
Yeah. Okay. Just to be sure. Yeah. Next time you just can open your microphone. Don't worry about that. So here, that is like so simple way to simulate those genotypes. So remember that as we are going to do linear regressions, we can use different codes to generate the genotype. So we can use 0, 1, or 2, and that means that we're going to increase one allele, that is dominant allele. In 0, we don't have any dominant allele. In 1, in the heterozygous, it's represented by the 1. So that means that we have one allele of the dominant, and in 2, we have the homozygous for that genotype. So you can see here we have the genotype for allele 1, 2, and 3, for locus 1, 2, and 3. And they are in Harding-Weinberg equilibrium. The way to check that, if you want, is just taking into account or add into account the.
Excuse Paulo.
Yeah.
I'm seeing x1, x2, x3, and I'm seeing size 2. Size is equal to 2. What does that mean?
Because we want to produce the number between 0 and 2, basically. That it's like the simple way to explain that. So as in the genotypes, we are going to have 0 for the recessive homozygous, 1 for the heterozygous, and 2 for the dominant homozygous. So that is why we have to produce that size. And the probability is the allele frequencies that we just put here, that is 0.5. Okay. And why we want to do that? Because we want to produce, and that again is a simulation, so that is not the real life. We want to produce markers that are a locus that are in Harding-Weinberg equilibrium. And remember that the Harding-Weinberg equilibrium is P squared plus 2PQ plus Q squared. So that is why I'm doing, we are using this code, because basically I just want to remember you all the concept that we saw in the videos. So as you can check here, if we take into account only the recessive homozygous that are represented with 0, that is, let me clean this. Of the 10,000 markers, that 10,000 genotypes that we just simulate with this code, with this pretty straightforward code, we have 2,500 individuals that are homozygous for the recessive allele, around 5,000 that are heterozygous, and around 2,500 that are homozygous for the recessive allele. And as you can see here, that it's the expected frequency that we are expecting with under Harding-Weinberg equilibrium. So remember that to estimate the Harding-Weinberg equilibrium or the expected number of individuals under Harding-Weinberg equilibrium, we have to use P squared times the size of the population. And as you can see here, under Harding-Weinberg equilibrium with P equal to 0.5, so allele frequency of P about equal 0.5. Do you have a question, Emmanuel?
Still, I didn't get the explanation earlier on better clearly. Why size is equal to 2. I think you may need to go over it again.
Okay. So yeah. If you want to get like a more complete, just to be sure that everybody is getting that. If you want a really detailed explanation about the variables that we're gonna discuss in the code that we're gonna use in RStudio, you can go into the function. In this case is R binomial, and you can chat, and you are gonna have an easy help access or access to the help here. So we are gonna show you here what are the variables that you can use in each of the functions that we're gonna use. So for example, here, this is the help that we have with a R binomial. And what the first number represents the size of the population that we're gonna use. So basically it's the number of observations. And here we have the number of trials. So basically what we want to produce is number between 0, 1, and 2. And that is why we are using the number 2, because we are gonna have 3 genotypes, starting with 0 for the recessive homozygous, 1 for the heterozygous, and 2 for the dominant homozygous. So that is why that size should be 2. And the P is for the probability that we are gonna use, that is the allele frequencies. Okay, so, but that it's a good question. I think that obviously for time, I am not gonna be able to cover up everything, but just be aware that you can go into the help that have R and especially RStudio, and you can read here in the help every single thing that I use in the code. And that is a really helpful way to not just improve your skills in R, but to understand every single part of the code, okay? But the pretty straightforward answer for that is we need to generate number between zeros and twos because we have 3 genotypes, okay? So yeah, as I mentioned, we're doing this just to generate the genotypes under Harding-Weinberg equilibrium, the locus under Harding-Weinberg equilibrium. And then what we need to do is create the genetic effect that we are going to have in the population. So the genetic effect, remember that it's the mean of the population that we are going to use. That it's in this example 5,000. And then what we're going to do is that the individuals that are homozygous, that have the dominant homozygous for the allele A1, are going to have the value of the additive value for that. Are going to have the additive value for that first locus, that is 1,000. Okay, so that is what I am doing here. So if the genotype X, the locus X1 is equal to 2, the phenotype or the contribution of that locus to the phenotype is going to be equal to the additive effect, that is 1,000. Then what I'm going to do is that if the X1 is equal to 1, that is the heterozygous genotype, the effect of that locus to the phenotype is the dominant deviation, that in the case of the first locus is equal to 0. And if the locus doesn't have 2 or 1, it's because that locus have 0, so it's homozygous for the recessive allele. The effect or the contribution to the phenotype is going to be the negative A1. So remember that in the additive effect, we have alpha or the additive effect. So, and the expected value of the heterozygous lines are right in the mirror of the phenotype. So that is why I have positive A, negative A, and the dominant deviation. So if there is no dominant deviation, it's because the heterozygous it's right in the midpoint between the homozygous. And we can do exactly the same with the second allele. And with yeah, exactly the same. The only difference here is that the dominant deviation in the second allele, it's equal to 800 because there is a complete dominant for that locus. So if you run that, then you can estimate you can obviously watch watch the data here. So as you can see here, now we have the mean of the population plus the contribution of every single allele to that phenotype. And we can with that estimate the genetic variance of the population, and with the genetic variance and that put together the question from Antoine. With the genetic variance, we can put together the genetic variance and the environmental variance to estimate what is the error variance in the population. So for that, now that we have the estimation of the genetic variance, we can estimate the environmental variance taking into account the heritability. So that is why this is a broad sense heritability, because basically this, yeah, we are checking all the heritability, all the variance that is explained because genetics.
All right.
Okay. Okay, so, and after estimate the environment variance, we just can estimate the error in the phenotype. And that to do that, we are just gonna create a normal distribution of the data with the size of the population that we have and the standard deviation that we identified in the environmental variance. So that is just to capture all the environmental effects and distribution and basically assign that environmental effect randomly in the population. And as you remember, the broad sense heritability is just equal to the genetic variance divided in the phenotypic variance, and the phenotypic variance is equal to the genetic variance plus the environmental variance. So if you do that, you can estimate that with the simulations that we did, the heritability is equal to 0.51, and the heritability that we the theoretical or the true heritability is 0.5, so it's pretty close. And as bigger is the population, the number that you estimate here, for example, for the broad sense heritability, is going to be closer to the real heritability, that is 0.5. So, but what happened if you want to estimate? Could you, there is one microphone that is open. Okay. So, but again, Antoine, if you want to now estimate the narrow sense heritability, what you have to do is remember that the narrow sense just take into account the additive effects. And why the additive effects? Because that are the effects that are you can transmit to the genotypes can transmit to the offspring, because they transmit just one allele, they not transmit the the genotypes. So for that, you have to I cannot mute everybody. Okay, so for that, you just can run the same model. Here we're gonna take in this variable just the additive effect, and as you can see here, we are not gonna take into account the dominant deviation. So if you do that, you can estimate the additive effect or the narrow sense heritability in this trait that it's equal to 0.42. So as you can see, the narrow sense heritability always is lower than the broad sense heritability, and the difference is because non-additive effects, in this case for the dominance effect, and as we have just one trait that is controlled for two, there is one microphone that is open. Faida, could you mute yourself, please? Okay, thank you. Yeah, so as we have more not additive effect, obviously the difference between the narrow and the broad sense heritability is going to be bigger. And as here we only have two locus, two loci that control the phenotype.
D'accord, merci beaucoup.
Yes, so we have just two alleles that control the phenotype, and one have a complete dominance effect. So that is why there is an diminution. Yeah, the heritability it's lower. Antoine, you have a question?
Yes, please. Can you please elaborate more on the rough estimate of both broad sense and narrow sense heritability?
Yeah,
yes.
sure.
Broad,
So remember
68 and 75. Thank you.
Could you repeat the last part?
I would like you to elaborate more, to explain more on again. Please come again on the rough estimate of both
Okay.
locus broad sense heritability and narrow sense heritability. Thank you. Okay,
yeah, remember that for the broad sense, we have to take into account all the genetic variants, that it's because additive dominance or an epistatic relation between the marker, between the loci, and we have to divide that with the phenotypic variance. So the phenotypic variance, it's due the genetic variance plus environmental variance. So that is what we have here, basically. In this genetic variance, we took into account all the effects. So we took into account the additive and the dominant effects. So that is why here we have, and this is a pretty simple way to show you the concept, because we just have two loci that control the phenotype. So that is why it's pretty simple to show you that here. So we're taking into account the additive effect plus dominant deviation. So we're going to take taking into account additive and non-additive effects. So, and that it's G. So the variance of G, that is the genetic component that is playing the phenotype, divided with the genetic component plus the environmental effects, that is the variance in the phenotype. So this variance here, variance of the genotype plus environment, is the phenotypic variance, because remember that the phenotype, it's basically the effects of the genotype and the environment together. So that is the broad sense heritability. But if you are interested in the narrow sense heritability, remember that the narrow sense only take into account the additive effect. and you have to divide those additive effect over the phenotypic effect, the phenotypic variance of the population. And again, the phenotypic variance of the population, it's take into account all the genetic components, so additive, dominance, and epistatic relation between the markers plus the environment. So that is why here in this line of I just take into account the additive effect, and the dominant deviation is equal to 0, because I'm just trying to estimate what is the additive variance that explain that yeah, those two locus in the population, those loci in the population. Okay, so that is the difference. So remember, in theory, the broad sense is all the genetic variance over the phenotypic variance, and the narrow sense is just the additive variance over the phenotypic variance. Okay. Yeah, Winifred, do you have a question? Yep. Okay. So, and again, for example, here, Antoine, we're going to estimate the phenotype, and the phenotype it's equal to the genetic effect or genetic component plus environmental component. And so if we run that, then this is just a command line to split the window to plot the graphics in 4. So yeah, that it's not relevant for the analysis. It's just to show you the 4 graphics in the same window. But what I want to do now is plot the effects of the 3 allele locus in the population. So as you remember, the first locus has a complete additive effect, and you can see here that the heterozygous lines are just in the middle, and there is some variation, and that variation is because environmental effects. So that is why it's not just a single line or a single point. That variation is because there are environmental effects in the phenotype that affect the phenotype. And the second locus, has a dominance effect. So the heterozygous lines are equal to the homozygous lines for the dominant allele. And the last locus doesn't have any effect in the phenotype. And as you can see here, they are basically, yeah, there is no difference in the phenotype if they are homozygous or heterozygous for the genotypes. And that is the distribution of the phenotype that we have. Okay. So, but I told you that another concept that we discussed here, you can see that there is an effect of the genotype in the phenotype. But something that we discussed a lot in the slides was the estimation of the allele substitution effect. And the estimation of this effect of the alleles, you can do that estimation with just a linear regression between the phenotype that it's Y and the genotype. So if you are interested to estimate the effect of the allele substitution, you just have to do a linear regression. And in R, you can use just LM to do those linear regression. Again, if you want extra help, you can go to that help here in RStudio, and they are gonna give you all the information of that function LM to run whatever you need to run with that function. And then what we're gonna try to take into account is the dominance effect. So here we just do a linear regression between the phenotype and the genotype. But if we are interested to estimate the dominance effects in that locus, we have to take into account as well the heterozygous. So this is a domain variable just to replace all the data sets, the matrix of the genotypes, and just keep the heterozygous line. So that is going to allow us to run the model with the genotype of 0, 1, and 2 that represent the 3 genotypes, plus the effect that have the heterozygous. So that is why we basically here replace everything that is not equal to heterozygous with 0. So here we are gonna assess the effect that have only the heterozygous lines in the population, because if they have an effect, so that means that it's gonna be a dominant deviation in the effect of that locus. And then we just have to run the same for locus 2. And the same for locus 3. And I'm just gonna run the locus 3 just to show you that as it doesn't have any effect, so the linear regression should be, so this slope should be equal to 0. And so now again, we have the same effects of the locus 1, but now this red line represents the linear regression between the phenotype and that genotype, or the genotype for locus 1. So we have the locus 2, the linear regression, and the locus 3. So as you can see here, for locus 3, as there is not any effect of that locus in the phenotype, the slope is basically equal to 0. There is not an effect of the locus. And this is a beautiful example, the locus 1, of the additive effect that we have in the phenotype. And the linear regression, you can see that fit pretty well the phenotypes, or the effects in the phenotypes. And this, I think that Antoine asked me that like 1 or 2 weeks ago about why we're using linear or additive models when we know that those models don't capture all the genetic variants or the genetic effects in the phenotypes. Well, as you can see here, although this model is not perfect, because here we have a dominant deviation, you can see that the models can capture pretty well that variation. Basically, we're able with the simple linear models to capture, to estimate which genotype is the worst, and what is the effect if we increase the alleles. If we increase the allele, in this case, the dominant allele in that locus. So again, the model is not perfect, but it's straightforward to use it, and it's helpful to predict the genetic value in the lines. Okay, and so then with that information, with those linear regressions where we estimate the slope, so I didn't show you that, but we have, with the linear regression, we have the intercept, that it's basically the phenotype when the value of the locus is 0. And then we have the effect of the slope, that is the additive effect. And then we have the dominant deviation, or the effect from, because dominants that have that genotype. So look that for the locus 1 that doesn't have dominant deviation, the effect of C, it's pretty close to 0. But if we do that for the second locus, the second locus that have a dominant deviation, you can see here that the model still can capture, when we take into account the dominance in the model, we can capture that dominance as well. Okay, so here in this
SD6 sama SD. Samir.
in this table, yeah. So this command, Antonia, do you have a question or that
Yes, please.
Okay.
Yes.
Sorry, it's
Yes,
because sometimes I don't know if your hand it's just there or okay. Go ahead.
Can we please go back where we had the plotting? Yeah, box plot. Yeah, before. Yeah, just
This
before the
one?
box plot.
Before? No.
I'm talking about codes. Huh? The commands. Box
Oh,
plot.
okay. So
Yeah. Here. Yes.
mhm.
No, you have done. You have gone far.
Uh,
I'm talking about the command here. The code par row
okay.
84.
Yeah.
Yes.
Yeah. Don't worry
84.
for that. That is
What
just
does I can see mf row equals concatenate 2 and 2. Then mai equals concatenating like 5 times 0.35. Can you please explain what
that don't
is
worry
that
a
for?
lot. That is just if we don't take into account, for example, here, if we don't use that command, you're just gonna have one graphic in the window. So as I want to show you all the graphics in the same window, that is why I use this function. That function, it's for a plot function. And basically what I'm doing here with command true is that we're gonna have, I want to split the window to make the plot in 2 rows and 2 columns. So that is what that means here. So basically I'm gonna split the plot window, that is this one. As I know that I'm gonna use 4 plots, different plots. So I'm gonna split into columns, 2 rows, and that is going to give me the space for the 4 plots. And this is just the margins, the margins to fits a little better the graphic. So that is just a graphic parameter to show you the data, but that doesn't have any relationship with the analysis. Yeah, but it's just to do that. So here we have this is the first row, and this is the second row that we use here. So this command is really useful if you want to put several plots in the same window, basically. Okay. And that is why I'm using the same command here. Yeah. So yeah, but what I want to discuss here is that, again, the additive models are not perfect, but they capture very well the dominant deviation. And as breeder, what we want is use those estimations in the real world. So the models works pretty well. And again, there are a lot of Bayesian models, for example, that are trying to capture some dominant deviations. And in theory, they are good as well. But the difference between, so far as I know, the difference between the models that just take into account additive effects plus the models that they try to capture more complex genetic effects, are the difference in the predictions are not that big. So I think that I have to move on because we don't have a lot of time. So with the linear regression, we can just estimate the effect of the phenotype that it's because that genotype. So here I just put some comments that basically I just extract the information from the slope that just take into account the additive effect plus the dominance. And here, as you can see, the expected value. So this is the real data that we have in this population. And here in this table, we have the expected value of that population with the genotype that they have, that the lines have. So as you can see here, under an additive effect that has the allele 1, so the heterozygous lines are just in the middle between the both homozygous. And in the second locus that have an dominant effect, you can see that the heterozygous lines are pretty similar that the homozygous lines for the dominant allele. And when the markers doesn't have any effect, so we don't expect that there is difference between the 3 genotypes in the case of locus 3. And here I just this last part of the code just show you how you can test using an ANOVA if your model first, if your model have an additive or dominant effect. So if you have a genetic effect in your for that locus, and as you can see that in the case of the locus 1, we have a really small p-value, so that means that there is a genetic effect in the population. For locus 2, we have the same low p-value. And for locus 3, that is the allele that doesn't have any effect, as you can see here. And that is for chance. Actually, it was pretty close to 0.5. That is the magic threshold. But yesterday that I run all the code just to verify everything, the p-value was like close to 1. So the point here is that just because I generate these numbers random, sometimes the p-value is going to be close to the significant threshold. But as you can see here, there is not an effect. So, and it's not lower than 0.5. So yeah, that is just another way to check if there is any genetic effect or no. And then if you want to check for a specific effect, so for example here, the locus 3 doesn't have a lower p-value than 0.05. So we are just going to continue using the locus 1 to check if there is a difference between the null hypothesis that it's just the mean of the population and the effect of the additive effect for the locus 1. And you can see here that the p-value is low, so there is an effect there. And the same for the locus 2. And then what we want to compare is, okay, no, we know that there is a genetic effect, but if there is a dominant deviation, so to assess if there is a dominant deviation, you just have to do an ANOVA between the model with the additive effects and the one that take into account the dominant effect. And if you do that, you can see that in the locus 1, that we only have additive effect. The p-value it's really high, so that means that there is not difference between those two models, so there is not a dominant effect. But in the locus 2, that we have a complete dominance effect, you can see that the effect of the dominance it's important, and we can identify that in the model. Go ahead, Antoine.
Thank you. I think I'm sorry, I'm asking many questions because maybe it is because unfortunately last time I was not able to get internet connectivity. I missed. As far as ANOVA here, is this ANOVA command is this ANOVA commands are concerned? I want please to know. Let's assume, for example, when we are doing ANOVA for testing whether there is an association, either additive or dominance or both additive and dominance. Can you please explain us from the data analysis outputs? Huh? What if it were this case, we should assume it means there is additive effect or there is a dominance. Do you get the question?
I think so. So do you want me to discuss about the?
Oh yeah, what I need is from the ANOVA outputs.
Okay.
From R. So I want to know when do we decide or conclude or know whether there is additive effect or dominance or both.
Okay, that is a great question. So yeah, I think that I was just so fast. I don't have any problem to stay a little longer because still we have two additional scripts to discuss. So if yeah, you can stay, everybody can stay with me, will be great. If no, the videos are gonna, yeah, I'm gonna load the videos of this session in the website. And this is the last session, so the videos are gonna be there for I think that 1 or 2 weeks. Just to let you know, because it's gonna take longer than what I thought. So yeah, your question is really good, Antoine. So the first thing that we have to do, it's set what is the intercept that we're gonna use as the null hypothesis. And that intercept is it's nothing different than the mean of the population. So we're gonna compare if the effect, additive or dominant effects are different to the mean of the population. So if there is an effect in the population that yeah, it's there. So with ANOVA, we are just gonna compare that mean of the population with the effect that we are gonna have in the model that we run with additive and dominant effects. So if we run that, you're gonna check that the p-value of a JAT ANOVA it's lower than a 0, is 2.2 minus 16. Okay, so that is a really significant, a very significant p-value. So that means that there is something there. So there is a difference, and there we can, as in this model, we have additive and dominant effect. We're just checking if there is any genetic effect. So here we just can conclude that we have a genetic effect in the phenotype. We are not sure about if it's just additive or dominant, but we are sure that there is a genetic effect. So we can do the same for the 3 genotype, for the 3 locus. And as you can see here in the locus 3, for example, this p-value is not significant, because remember that locus 3 doesn't have any effect in the phenotype, because we did that simulation that the locus 3 doesn't have any phenotype, any effect in the phenotype, and that is why the p-value is not significant. So in this, with this simple ANOVA, you can check the mean of the, if there is difference between the genetic effect and the mean of the population. So if there is any effect of those locus in the mean of the population. And we check that the locus 1 and 2 has effects in the population. As you can see here, the p-value is really, really small. And the marker 3 or the locus 3 doesn't have any effect. But with this, when you compare the ANOVA, or you use the ANOVA to compare the mean of the population with the genetic effects, you just can say that you have a genetic effect. You are not sure about if your effect is additive or it's because dominance. So what we're gonna do now it's that we're gonna test for the two markers when we got a significant effect of genetic effects. We're gonna compare that with the mean of the population, just the additive effect. So as you can see here, I just taken into account in this ANOVA the additive effect. And again, as both molecular locus has additive effect, you can see that the p-value is significant for both of them. So for sure, we have an additive effect in those two locus. But now, if you are interested, okay, I want to know if it's just additive effect, what we have in those locus, or if it's additive and dominant effect. So that is why in this ANOVA I compare the additive effect plus the model that take into account the dominance effects. And as you can see here with the p-value again, for the first locus that only have additive effects, so here there is not any dominance, the p-value it's really high. So that means that there is not a dominant effect in the locus 1. That is what we simulated. And in the locus 2, that is the one that have a complete dominant effect, you can see that the p-value is really low, and there is a dominant effect as well. So with this, you can conclude that locus 1 and locus 2 has an effect in that phenotype, and that locus 1 doesn't have with this ANOVA. Locus 1 doesn't have any effect in the phenotype, dominant effect in the phenotype, and locus 2 also have an additive and a dominant effect in the phenotype. Okay. I was clear, Antoine?
Yes, I'm not comfortable. Thank you.
Okay, great. So now what we're gonna run so now we have another script. Again, as I told you at the beginning, I changed some things in the code. So I'm gonna load the code this afternoon in the website again. And for example, I didn't put this part in the code. Now we're gonna use a multiple allele effects in the phenotype. And for that, we're gonna need some R packages. And if you are not familiar with the packages, so you have to install them, and then you have to load them into your R session. So the way to install the package are just install that package and the name of the package. I am not going to install them because they are already in my computer, but I have to load the packages. So if for some reason the code is not working in your computer, please check if the packages are installed in your computer. So this first part, the library and the name of the package, is just to put that piece of software into your R session to use the tools that have that have all of them. And now we're gonna do our lives a little more difficult. So we're gonna produce again genotypes, but now we're gonna produce more data. So the first thing that we're gonna do is just create a matrix, and this matrix is just gonna have zeros in that matrix. So you can watch the matrix here. So it's just a matrix with zeros, and we're gonna simulate 1,100 markers with 500 individuals. Why? Just there is not reason for that, just because I wanted to do those numbers. And we're gonna use a for loop here, and that I try to don't use a lot of for loops because I don't know if you are so familiar with that, but some cases I just cannot avoid to use the for loops. But a for loop is just a way that has R to repeat the same process multiple times. And what I'm doing here is just putting or filling the matrix that we just created with just zeros, and I am putting minus ones, negative ones, and positive ones into that matrix. And that negative ones and positive ones are going to represent the homozygous genotypes that we're going to use for our analysis. So as you can see here, now we have a matrix that was just with zeros, and I fill that matrix with positive ones and negative ones that again represent the genotypes that we are going to use in the analysis. And we're going to put some names in the columns of that matrix. So you can see here that the original matrix didn't have any names. And now we just have the names that are consecutive numbers as names in this data in this matrix. And this part, yeah, I think that it's very interesting maybe for you. So we can create with that information a data frame that is an object in R when we're going to have these columns, so columns with information of the SNPs, with information of the chromosomes, and with the position, genetic position of each single marker with the position in the genotype. So if we run this command here, you can see now that we have one column for the SNPs, one column for the chromosome, one column for the position of each single marker in the chromosome, and then we have the genotype. So that is the matrix, the genotypic matrix that we're going to use. And then we want to create the QTRs, because the point here, or what I want to show you, is that it's not easy to detect all the QTRs in the population. So we're going to create 20 QTRs, and that command here is just to set some physical position of the QTRs, and then I'm going to assign the effects of every single QTR. As in total, I have 20 QTRs in the population. So as you can see here, I set a effect of every single QTL in the phenotype, starting with 20, and the major QTL, or the QTL with the highest effect in the phenotype, it has an effect of 400. So yeah, that are just the effect of the QTL. So this command here was just to estimate to define the position of the QTRs, and this command here is to give to each QTR an effect in the phenotype. So then what we are going to do here is the cross product between the molecular markers and the effect of the QTR. So as we define with these two commons, the position and the effect of the QTRs, so we're going to produce the effect between those markers and the QTRs in the population. And we're going to use a heritability of 0.6. And remember, I'm using the heritability just not just to remember you that is important for the analysis, but also to because with the heritability, I'm able to produce the variance or to take into account or to estimate the environmental variance. So as in this example, the genetics explain the 60% of the variance of the phenotype, the 40% of the variance is because environmental factors. So here I'm using the generic effects that I just estimate with the cross product between the matrix of the molecular markers and the QTR effects. I'm going to produce a random distribution of 500 individuals with a mean of 4,000. And here, as you can see, the standard deviation of this phenotype is going to take into account the heritability of the trait. And with that information, now, as you can see here, just I put yield to this trait just to have a name. And as you can see here, the distribution of the trait it's close to the normal. And then I just run this code here to put a data framework that is another object in R when I'm gonna have the name of the wheel and the phenotype of every single wheel or line in your population. And so GWAS, here is a function of the package RRBLAB. And yeah, so if you don't have RRBLAB in your computer, if you didn't load the package, so you cannot use GWAS, so, this function. So that is why you have to install and load the libraries. But here with this function, you just have to feed that function with the phenotype and the genotype, and that is going to estimate the it's going to use the mixed model to estimate the association between your phenotype and your genotype. So it's pretty fast. And with that value, as you can see here, so you are going to have the information of the SNPs, the chromosome, the position, and here the yield. This GWAS function doesn't change the name of the trait that we're using to do the GWAS, but here basically this is the minor logarithm of the p-values that the function found in association with the phenotype. So that is the output of the function, basically the association between each single marker and the phenotype. And then basically I'm doing that because I need to transform back the values to p-values. And what I'm intending to do here is doing the Manhattan plots to show you the association with every single marker. So as you can see here, every point that is green, it's a real QTR. So remember that we use some marker effects, QTR effects that starting in 20, in this case, kilograms, if we are talking about yield, and the last one have an effect of 400. So those are the effects in the phenotype. But as you can see here, we have 20 real QTRs, but we are just able to detect in this example 1, 2, 3, 4, 5, 6 QTRs. So from 20 QTRs, we just able to detect 6, and that it's a really common problem. And what I want you to see here is that we are just able to detect using QTR, using GWAS association mapping, and actually QTRs as well, alleles that are has an important effect in the phenotype. So the QTR that have, or the minor QTRs, are really difficult to detect using association mapping and sometimes as well QTR analysis. So that is what I wanted to show you with this graphic. And I think that here we don't have to discuss this part because basically it's the same that we did in the previous slide. I'm just gonna go faster here. But it's just basically the values that we have, the expected value that we have when we use the data from the QTF that have the highest effect in the population. So as you can see here, the effect of the QTF with the highest effect is around 400 kilograms. That as it's the value that we simulate. And here, for example, it's the effect of the major QTL that we have when it's recessive for the homozygous line, it's homozygous for the recessive allele and homozygous for the dominant allele. And this blue and red line is the difference between the mean of the population with both genotypes. What else? And yeah, and this last part is just gonna show you another way that I put in the code. So this CM plot is just another function from another package that is CM plot. Basically, that is the name of the package. And this package, it's a nice way to produce graphics. So circus plots, if you're familiar with them, are pretty fancy way to produce Manhattan plots. The bad thing with that package is that it doesn't print the graphic here in the R console. So basically they are store those graphics in the folder when you have the data, when you have the R script. So let me show you the graphic that you can produce with that. So with that command, you just can produce this circle. Can you see the circus plot or no?
Yes.
Okay, so you can
Yes.
produce this graphic. I think that it's fancy, but I don't know. Some people like it, other no. And this graphic is so silly here because I just repeat. I am using the same trait, the same phenotype that I simulate to do several rings. So that is why it's basically the same several times. But it is used for example, if you are using GWAS for traits that have a correlation. So those traits that, for example, ER components that they are controlled several times for so several locus control the that phenotype. So there are several regions that have effect in different phenotypes. So it's nice to see if those regions are the same for different phenotypes, because there are regions from interest in breeding. So with this last part of the code, you can graphic this kind of trait. You can do this kind of graphics that are circus plots. So yeah. And the last, we're almost done. So sorry that take me so long. And now we're gonna do we're gonna run the script for genomic selection. So let me bring some water that I need to drink water. Give me 1 minute, please. Okay, so the last part is again about genomic selection, and we're gonna need basically the same packages that we use in the previous code. And again, just as good practice, you should to remove all the, if you are gonna start to run a new script, it's good to remove everything from your global environment, and then basically just run all the packages that we are gonna need. And in this part, I have exactly the same code that in the previous script, and basically we are going to need that information because we are going to use the same genotype that we produced in the previous code to run the genomic selection models. So here now what we're going to do, it's in the genomic selection, the first thing that we need to take is the phenotypic data. So remember that we have this phenotypic data here that was the same that we produced in the previous slide, in the previous script. Basically, we have the line and the phenotype. So we're interested just in the column 2 that are the phenotypes. And we're going to scale that phenotypes, and because in theory, in genomic selection, when you scale the data, you are able to capture more of the additive effects of that data. So you can run the model with the raw phenotype if you prefer that. That shouldn't be a lot of difference, but actually yesterday that I
Let's
was
go back there.
But yeah, yesterday that I was running this code, I saw that there is a difference if you run the code with without the scale the data or after scale the data. I have some questions in the code in the chat. So Maria asked about perform analysis GWAS and genomic prediction with an orphan cross with no information about pedigree and chromosome positions. For the genomic selection, I would like to predict for untested environment. So yeah, I think that we can discuss that, Marian. Yeah, after the session, if you have time, because yeah, that it's about your project. Okay. So yeah, so in theory, if we scale the data is just subtract the mean of that phenotypic data in this case, and they divided that into the standard deviation. So there are two constants, and what Alice or the advantage to use that is that basically your data is going to be it's going to be easier to work with your data. So here we're just extract the phenotype that we're going to need, and this is the So check here that now we scale the data. We don't have a different typical data that is between 1,000 and 6,000 that actually we can do that right here. So here you can see that basically we don't change the data. The data is exactly the same, but we change the in this case the y-axis values. So the original data was between 1,000 and 10,000 or more than 10,000, and when we scale the data, as you can see here, now the variation it's smaller, and seems that when we scale the data, it's easier to capture the additive effects. So that is why we're going to use we're going to scale the data here. And so then we need to put together the phenotype and the marker effects. So when we produce the molecular markers, we set 1,000 rows and 500 columns, but the phenotype has a different scale, a different dimension. So dim is just a function to identify the dimensions of the data sets. So as you can see here, in the phenotype, we have 500 rows and just one column, and we cannot put together this data. So that is why, because they have to have the same rows to put together. So that is why we have to transpose the molecular markers, and to transpose the data, we just have to use T. That is a function to transpose, to change the column to rows. And now we have the same dimension. So we have the same rows for the markers and for the phenotypes. And this part, it looks horrible, but yeah, I didn't use any for loop because I want you to understand this concept, because I believe that it's really important. So remember that we have 20 QTLs, and here we have the positions of those QTLs. So the first QTL is in position 55, the second one position 110, and until the last one is in position 1,100. And then we have the effects of the QTLs, and we know that, and it's easy to know that because we simulate the data. So we have a molecular marker, for example, the QTL, for example, in position 55, only have an effect in the phenotype of 20. So now what we're gonna do, and I think that Winifred once have a question about that, is that we're gonna set some fixed variables to use in the model. So remember that in the videos we discussed that in genomic selection, usually we use the molecular markers as random effects. But if you have some QTL that have a really good or have a effect in the phenotype, you can use that information as fixed effect in the model. So if it's a major QTL, so the effect of that QTL could be affect in a positive way the predictions of your models. And in this same way, you can also fix, for example, environmental variables or the year or any variable that you want to use as fixed effects, so you can use in the same way. So that is why I think that it's important. So as we have 20 different QTLs, I'm just gonna use, I'm gonna create that is just to create vectors with the position of the QTLs that we simulated, and it's again looks pretty bad, looks awful, but again it's just to show you how you can put together this data. So here, for example, index QTL1 is just nothing different than the position of the QTL with the highest effect. Index QTL2, it's just a vector with the position of QTR1 with the 2 QTR with the highest effects, and I just do the same until the last index QTR take into account the position of the 20 QTRs in the genome that control this trait. So remember, this trait just have it's just controlled for 20 QTRs in the genome. And then, as we are going to use that information in the as fixed effects, we cannot use the same information as random effects. So we have to remove those columns from the information from the markers, because we just cannot use the same information in fixed and then in random effects, because that is going to overestimate the outcome or the variation that explains the model. So that is why now we are going to use those index, and we're going to remove that for the marker effects. So basically, we're going to create 20 different data sets, and in each data set, we're going to use different fixed variables. Go ahead, Antoine.
Thank you. What do these values mean? QTL index. What does it explain?
That is just a name that you can use any name that you want. I just assign this vector of numbers to that variable. So the index QTL 20, it's just something that is easy to remember me what I'm doing here. But the important part here is the vector.
My question is, yes, these values, yes.
Those
that's
are
where
the,
I use my question.
Those are the QTL positions. So remember that we have 20 QTLs with those effects, and those are the physical position of the QTRs. So what we're going to do here is that the index QTR1 only have the physical position of this QTR here, so this physical position, and that QTR have an effect of 400. So that is why I started using the QTR with the highest effect. That is the one that is in position 1100 as fixed effect here. And then the second data set is going to have two fixed effects that are the QTRs in position 1045 and 1100 that have the highest effects in the position. So basically, or the short answer is that those numbers are just the physical position of the QTRs that we're going to use as fixed variables. So, and we are going to compare what happened if we use all the molecular markers as random effects. That is the usual way that we use in genomic selection. What happened if we use just one fixed effect? What happened if we use two fixed effects? Until what happened if we use all the QTLs as fixed effects? So that is what I want to show you today. Okay. Yeah, but Antoine, these are just the physical position of the QTLs. So just look that I started using the QTL with the highest effect, that is the QTL that have 400. And the second one, I include another QTL with the highest effect. And then I started to include every single QTL because their effect in the phenotype. And the last index 20 have all the QTLs in the genome. Okay. And again, I have to remove oh, I think that I make a mess here. Go ahead, Anton. Do you have another question? Sorry, Arfan.
It's Arfan, yeah. So I was wondering, in determining, hello?
Yeah, go ahead.
I was wondering in determining the position of each QTL, how when you have, because I know the QTL should be at a particular chromosome and at a particular position on that chromosome. So I don't know how does that the position, the chromosome and the position and the physical position, how does that appear on the different positions you have given on the indexes?
Mm,
Like if I had my QTLs, each QTL is on a particular chromosome and on a position on that chromosome. How do I get that information here for the model to be able to find the exact QTL I'm referring to?
that it's a really good question, and I think that hopefully, no. What is the name of? Yeah, well, I don't remember the name of the variable that I used for, yeah, was, mhm. Just show, let me show you this. So you are right, the thing it's here. So we have a matrix of 1,100 markers. And here, basically remember that I named the ID of the marker just with a consecutive number. So the first molecular marker that is in chromosome 1 in position 1, it's the ID, it's just 1. Yeah, because it's easy for the simulation. If we go to the end of that genotype, we're gonna have you are gonna have that the last molecular marker is with the ID of 1,100 in position in the chromosome 11 and in position 100. So you are right, you are gonna need to fix the variable. You are gonna first obviously identify the QTL, identify the chromosome and the position, but you can use the ID or basically here, as you can see here, the position, the number of the row is the same that the SNP name that I use. So basically what I'm doing here to fix the variable, it's just the a column actually, because I have that information in the column. But it's using the order in which I have the SNPs in the matrix with the molecular markers. So I don't have to specify, for example, if you have this QTL in chromosome 11 position 91, I don't have to, it's more difficult to specify it in the code that you need to fix the marker in chromosome 11 position 91. It's just easier to set that you want to fix the marker that it's in the row 1091. Yeah, I was clear. It's just because for
Yeah.
yeah, it's you can use
I think
yeah, you can use
I
the
think I
order
get
that
it
you have.
now.
Sorry, go ahead.
No, I mean, I think I get it now. Thank you very much.
Okay, great. Yeah, it's just because it's easier, but you are right. So you need to know, you need to identify chromosome and position, but then when you identify the ID of the marker, you just can extract that information using the column or the row, that depend on how you have your data. Okay. So I think that I was here. Yeah, now we have to remove that fixed effects from the molecular markers, because all the molecular markers, we're going to use all the molecular markers as random effects. And yeah, because if we keep that in random and fixed, that is going to cause more noise, and we don't want that. And And then we are going to create a new variable. And again, this could looks a little difficult because we have different data sets. But the point here is that now we want to create a matrix that have just the fixed effects that we want. And to do that, again, we use the index QTL that we created that is nothing different than just the physical position in our data set from the fixed variable that we want to do. And we're gonna check that information from the marker data set. So as you can see here, we are gonna have that it's gonna extract the column 1100 from the dataset markers that the dataset marker the dataset marker, remember, that have 500 rows and 1100 columns. So here basically we are just doing we're just gonna extract the column 1100 from all the data set of markers. And with that, we're just gonna have one column. Oh, what I did. So we're just gonna have one column that, sorry for that. We're just gonna have one column that have the fixed value, that we want to fix. Okay, and we're gonna do exactly the same for all the other 20 data sets that we have, and the last data set that are the one that have the information, the genotype of the 20 QTLs. It's gonna have 20 columns, so that we're gonna use the genotypes of those 20 QTLs as fixed variables in the model. So always take a lot of time to organize all the data to fit the model, but when we organize that data, the model, it's kind of straightforward. So then in genomic selection, we have to run several cycles or repeat the process several times. And that it's because to try to estimate the allele effects in the population, that is gonna depend about the training population. So what we are gonna do is select randomly some percentage of the population, and we're gonna use that population as training population, and we're gonna predict the phenotype in the remainder individuals in the population. So if you remember the concept of allele substitution effect that depend on the allele frequencies, and that is why the training population, so the genotypes that are in the training population are going to produce or can produce different estimation of the allele substitution effects. So that is why repeat the process several times is going to give you a better idea about how good is your model. And I just going to use here 10 cycles because I don't want to take a lot of time to run, but usually what I do is use 100 cycles. So that are just the number of cycles, and here I'm just gonna create an empty matrix to start to store my data. So you can see here that it's just an empty matrix of 21 columns. So it's 21 because in the first column, I'm gonna store my prediction when I use all the molecular markers as random effects. The second column is gonna have my prediction when I use just the QTL with the highest effect as fixed effect, and the remainder markers as random effects, and so on until the last column is gonna keep the prediction, it's gonna start the prediction when I use the 20 QTLs as fixed effects in the population. And then I'm gonna use a for loop that is again repeat the process, and where I gonna create a training set. So that training is gonna be training population. So I'm gonna select 250 individuals. So I'm gonna use 50% of the population to estimate the allele effects in every single locus, and then I'm gonna the remainder individuals in the population are gonna be used as testing to test the model. Okay, so that is just gonna give you 2 data sets of numbers, and we're gonna select in the rows those numbers to run the model to estimate the allele substitution effect, and then the remainder of the samples are gonna be used to estimate the prediction of the model. And here, with that information of the training population and the testing, we're just gonna extract the phenotype and the molecular markers, because that's what we want to do. So we, after identify the training population, we have to take apart the genotype and the phenotype of that training population. And we're gonna use the same for the other 20 data sets when we're gonna use the fixed effects. And here, this is just to fit the fixed effects into the model. As I showed you previously, it's nothing different. It's just that now that we know what is the fixed effect, or the matrix with the fixed effect, we have to take into account now what are the samples that we are going to include into the training population and into the testing population. It's nothing different than that. And now we are gonna extract what, at the beginning, we extract the information from the training population, because we need the phenotype and the genotype to estimate the effect of the alleles. So now we have to extract the information of the phenotype and the marker effects to predict what is the accuracy of the model in the testing population. So that's why here we extract the information from the testing population. And after that, as you can see, that takes some time to figure out what is the training population, what is the testing population, but then you can run the model. Go ahead, Antoine.
Thank you. Do we consider, do we use 350 lines for the model, or I was expecting a 250?
In this case, we're going to have 250.
Yes.
But
yeah, no, you have gone far.
Yeah, here, and here is just a mistake. Yeah, here you are going to select I just want
150, row 156.
156.
56.
Yeah,
56?
here.
No, down.
156. This one?
No. I think I'm mistaken.
Yeah. No, I that was my mistake. You're right. I have.
Okay.
Yeah, I just modified. Right. I just modified that.
Okay. Thank you.
Yeah, but it was a mistake. We're gonna use 250 as in the training and 250 in the testing. But again, that is just because I want. Usually, a lot of papers use as training population 70% of the as training population 70% of the individuals in the population. Here I just use 50%, but remember that in theory, as bigger is your training population, better are gonna be your predictions. And the reason for that is because as more data you have in your model, the estimation of the parameters tend to be better. Okay. Yeah, but we're gonna use 250 individuals. And after said that, you can see that a mixed solve model is a function of RRBLOB. So if you need help, you can go here in RRBLOB. And if you remember, we discussed this model in the slide. So basically, the phenotype is equal to the fixed effect plus the environmental effects plus the error. So here in this first in this command line, we're just going to take into account the phenotype, and we're going to use as predictor all the molecular markers, and all of them are going to be random effects. So that is like the most common way to run genomic selection models. So using every single marker as random effects. And then we're going to use the other models that are going to take into account the different data sets that we create as fixed variables to feed the model with fixed variables. And as you can see here, the difference is just that in this second model, we're going to take into account the fixed QTLs to try to check if that of those QTLs has a positive or negative effect in the predictions. And we're going to use the same for the 20 different fixed effect or matrix that we are going to fit as fixed effects in the models. Okay. And yeah, that it's just going to run the mix that is on the RRBLOB model that we discussed on the videos. And that model is just to estimate the effect of every single molecular marker that you have in your genotype. So here I am using just the training population to do the linear regressions between the phenotype and the genotype and estimate the effect of all the molecular markers. So then when I have the estimation of every single molecular marker, what I have to do is predict the phenotypes in the training population, in the testing population. So to do that, I just can take into account the allele substitution effect that I estimate with the model and multiply that with the genotype in the training population. So remember, in the testing population, sorry. So remember that in the testing population, we need the genotype. We don't need the phenotype, but we need the genotype. We need the phenotype to basically assess if the model is good or no. But to predict the genetic values in the testing population, we just need the genotype. And we are going to put together that information with the estimation of the allele effects that we estimate with the model. So that is why here we have to multiply the genotype and the effect of every single marker. And that is when we have just random effects. When we have fixed effects, we have to do the same. So we have to take into account the effect of every single marker and multiply that with the genotype of every single sample. But also we have to add the effect of the fixed effects. So in this case, the effect that the QTLs have to explain the phenotypic variance of that trait. So again, we do the same for all the QTLs as fixed variables. And then we have to basically to say how good or bad is our model. We have to do a correlation between the predictions that are the predictions that we estimate with the models and the real phenotype in the population. And with that correlation, that it's basically the accuracy of our model. And after that, we are gonna do a mean, basically a mean of the accuracy in the different cycles that we run for that for every single model, and it's done. So that is the genomic selection model with fixed and without fixed variables. So hopefully it's gonna run. So it's gonna take some seconds, I think. It's not a large data set. So if you have questions, this is a good moment because we have to wait 1 or 2 minutes for the program. And this apply, it's just a function in R that basically it's easy to apply in other functions as the mean, because we are interested to estimate the mean of the population here. Go ahead, Frank.
No, I just wanted to make sure that I know what is going on. For each of the cycles, it randomly picks the 250.
Yeah.
It's just a random sampling.
Yeah, that is a really good question, because every time that you select, for example, the first time 250 lines, the model is going to estimate the allele effects using the information genotype and phenotype of those 250. But the QTLs are, you have different like environmental effects, different QTL information between those 250 lines. So they are gonna, the estimation of those 250 is gonna, of the allele substitution effect is just gonna be true for those 250. So then if you select other 250, the estimation can be a little bit different. So as closer, if the general relation, it's closer between all the lines in your population, the effect of this random selection is going to be smaller. But if you have subpopulations, if you have a really complex genetic background in that population, the prediction between different data sets, it's gonna be different. So that is why it is important, just to give you an idea how good is your model, it select randomly the population. So there are other methodologies that they are actually more efficient to select that training population that is taking into account the kinship between the lines. And if you are interested, I can share a paper about that. But there are more efficient ways to estimate, or to optimize the selection of the training population. But
I think it would be good to have something like that, including maybe when you consider the kinship between the population, within the lines, and maybe the structure within the population, and to be able to capture it in the genomic prediction models.
Yep, you are so right. You are so right, and that is important, and I am so interested on that, because as you can use like additional information as the pedigree, you also can use the pedigree for that, or the kinship. You can reduce a little bit your training population. Could be that, as smaller is your training population, if you cannot, as smaller is your training population and you still keep the same prediction accuracies, it's better for your program, because you just can plan your training population in different environments and different, and test different things. So the optimization in the training populations, is something that is important, and it's something that we have to test.
Okay.
So now with the apply function, we can estimate the mean of the prediction for every single model. So as you can see here, the model that take all the markers as random effects have a prediction accuracy of close to 25%. And the one that has all the molecular markers, the QTL as fixed effects, increase the prediction to 75%. So I think that this is just to show you what happened, that it's the generic, that is the linear regression, the correlation, the scatter plot between the real data set, the real phenotypes and the predicted phenotypes. So as you can see here, when we don't take into account the QTL information with this trait, the predictions are not that good. So that is why it will be good if we can take into account in this example the information from the QTLs. So what I'm showing here are the different accuracies of the models. So this the first box plot here represent the model that use all the molecular markers as random effects. And then as you can see that when I started to use the QTL information as fixed effect, the accuracy of the models tend to be better. And I just want to show you that it is important, if possible, use previous information, QTL information, GWAS information into your models. And also it's true that sometimes, so this is a beautiful example, but sometimes also that if the QTL are the effect of the QTLs are really not that big, instead of increase the prediction accuracy, they can reduce the prediction accuracy. So that is why it's something that I believe it's important to at least try. And yeah, that it's depend of your population and your crop and a lot of, and the most important factor is the effect of the QTL in the phenotype. So Dr. Rex Bernardo suggests in one of his papers that you should try to use QTLs as fixed variables just when they explain more than 10% of the phenotypic variance. If they explain less than that, they can reduce the prediction accuracy. But yeah, the take-home message here is that actually I'm trying to use that in my research, is that there are a lot of information available about the QTLs and GWAS. And if we can put together all that information into the models and try that information, and try what happened, that could increase the prediction accuracies. But again, the most important point is that the QTL is the effect of the QTL. Okay, as you can see here at the end that I started to add the QTL with really small effects. The effect in the predictions it's basically zero. And it's pretty cool, no? It's pretty cool that using fixed variables or information from other papers, in this case from the QTL that we were able to detect, we can use that information to feed the model and increase the prediction accuracy. And another kind of analysis that you can do it's just use the molecular markers to run the models. I think that is not a good practice, just because it is really difficult to detect all the QTLs. But in this part of the code, that is the last one, I just basically run the same code, but here I just use the information 20 QTLs. So this model only have 20, the information of 20 QTLs. And as you can see here, the predictions are great. So we can use that information or one model with this one in the breeding program. That would be perfect. But that is not so real because it's really difficult to detect all the QTLs that control quantitative traits. So yeah, so in theory it's possible, and that's why I wanted to show this option here, but it's really difficult to detect all the QTLs. So I am working in a meta-analysis in yield, and I have detected more than 620 QTLs. So as you can imagine, it's really difficult to identify all the QTLs that control something like yield, and the effect of those QTLs, it's not that big. So that is everything that I had to show you today. Thank you so much for your time. So sorry for take a lot of more time, 1 hour more. I just want to show you all the code, and hopefully that was helpful for you. And I'm gonna post the code in the website. And yeah, Antoine, do you have a question?
Yeah, thank you. I think it has just been answered. I wanted to ask whether you can share with us the codes. Huh?
Yeah,
Thank you.
sure. Yeah, I'm gonna post everything in the website. I'm gonna try to keep all the information there. If you have questions, you can use Slack. So Slack is for that. I really encourage you to interact between you. I think that this is a great opportunity to start to create a community. If you don't have a community, still in quantitative genetics, and it's still that it's a really good opportunity, especially for students, because there are a lot of breeders in this group. I think that would be great. And if I am available, I can try to help you if you have questions as well, using Slack. And yeah, I'm gonna post everything. The only thing that I'm not sure it's about the videos, because I'm using YouTube, and seems that in YouTube you have a limit of time, and I'm doing another activities as well. So maybe I'm gonna have to remove the videos, but the slides and the codes, that part is gonna be available in the website. I don't need to change that.
Paulo.
Yep.
Yes, as you promised to share the codes, I would request that you also improve on the comments that you attach to the codes. Let the comments be clearer as well to explain the codes when you share.
I'm gonna try. I'm gonna try to do that.
Yes,
okay.
yes, that would be very, very, very great. Just like some of the questions that Antoine was asking, because sometimes you see the code being run and you can't pick exactly what is what output is expected from that code, and something like that. So if the code can be additional comments can be attached, then it will be very clear. Then the other thing, I see most of this practical session has been mainly on genomic selection. It seems you left out something on the other bit that we handled in the videos. For example, things to do with the QTL mapping, those methods of simple interval mapping, composite. I thought they would also come up, but here it seems you've been biased mainly on genomic selection.
Yeah, Emmanuel, you are right. Actually, the course was, the original idea was just to talk about genomic selection, like a shorter course. That's what we just did. But I wanted to discuss more about QTL and GWAS analysis, because we can use that information in the models. But yeah, I am in the multiple allele, we run a little fast model to GWAS, but yeah, I am not intended to cover QTL analysis, for example, in this course. We discussed that because it's important. We discussed that because some of the limitation of QTL analysis, because some of the limitation of QTL analysis is why we want to work with genomic selection, but yeah. But what I can do is that if you are interested, actually I'm gonna post that in Slack for the people that is interested in quantitative genetics and GWAS, QTL, and that kind of analysis. In Washington State University, they have a really good summer. I think that the name is statistic genetics courses, and you have to pay for that. But the good thing is that the material for the previous years, it's available for free. So they have some information about QTL analysis, I think so, and GWAS analysis, and you can check that information. Yeah, if you are interested. Yeah, but the intention of this course was not discuss about QTL or GWAS, was mainly about genomic selection. Okay, there are more questions or comments. So today in theory is the last day, or in theory no, it's the last day. So if you have questions, I can try to help you with them. Again, I am not an expert at all, so that was something that I said at the beginning. I'm so happy to work in quantitative genetics. I think that is a really nice field to work with, but I'm learning, and thank you for this course, because and for all of you, because I learn a lot, and hopefully you learn something about this course as well. So yeah, again, I think that there are somebody that I asked me some questions. Mariam, if you are around, if you are still around, let me know if you want to talk more about that. And
Yes, I'm there. Dear Paulo, I'm there.
okay, great. And
I'm still waiting for the end of the session.
okay, sure. And
Thank you.
so yeah, that would be great. I am so happy that after 2 hours still we have people, so that is great. And again, all the material is gonna be there. I'm gonna try to comment more about the R code that they're gonna post. I encourage you to use RStudio and R Markdown. Something that I didn't show you is that with this knit, that is this part here, you can produce this kind of documents, and you can store that in a HTML or PDF in your computer. And that is a really a good way to share that information with your lab mates, and it's a good way to reproduce your data, so your results. So I encourage you to use. If you don't use R, it's a really good way to analyze data. It's free, so that is the best part of R. And the first couple of months maybe is a kind of hard, but after that, yeah, you are going to improve your skills a lot on that. Could we get more resources in the website? If you want, Marian, what I'm going to do is use this Slack, because in the website I have to do some code and update that in my GitHub account. But what I'm going to try to do is post some resources in the Slack channel. So hopefully everybody is in the Slack channel. So I'm gonna post some information there. So the information from Washington State, that again, you have to pay for that, but the information of previous year is available, and actually some videos from the previous years also are available in the website. So I'm gonna post that information in there. Okay, so if you don't have more information, if you don't have more questions, this is the end of this session. And again, thank you so much for your interest. Okay.
Thank you very much.
Okay.
Thank you.
Okay, Marian, if you want, I'm gonna need more water, so give me 1 minute.
Okay.